Hello, everyone, and welcome to this explainer covering Section 13.3 on security requirements. Think of this session as your professional university lecture, where we're going to dive really deep into the fascinating and frankly critically important world of secure software engineering. We simply cannot run the modern world without software, and because our systems are constantly under threat, understanding exactly how to specify requirements to protect them is an absolutely vital skill for any software engineer. So let's get into it. Here is our agenda for today. It follows a really logical flow that's going to prep you perfectly for your upcoming exams. We'll start by contrasting safety with security, and then we'll break down the specific types of security requirements. After that, we'll walk step by step through the risk-driven specification process, apply it to the Mentcare system example, and tackle a crucial concept known as misuse cases. Finally, we'll wrap up with a thorough lecture summary. All right, let's dive into our first major topic, safety versus security, and really understanding our adversary. To kick things off, we need to explicitly state a massive paradigm shift in how we think about software engineering here. We are no longer just dealing with accidental faults. We are dealing with deliberate attacks. Let's draw a stark contrast. In safety engineering, which you might remember from earlier chapters, we assume a non-hostile environment. We're just trying to prevent accidental failures or hardware glitches. But security is so much harder. Why? Because you are fighting an intelligent, adaptive human adversary. An attacker is actively probing your system's defenses, modifying their behavior as they learn about your setup, and deliberately trying to hide their tracks. Safety-related events are accidental, but security-related events are malicious and entirely intentional. Now, let's address a really common misconception that students often make. In a safety-critical system, if something goes wrong, the default safe action is usually to just shut the system down to prevent harm. Makes sense, right? But in security, simply shutting down the program is actually a terrible defense. Think about it. If your system automatically shuts down every single time it detects anomalous behavior, an attacker doesn't even need to break in to ruin your day. They just trigger that anomaly, the system shuts itself down, and boom, the attacker has successfully executed a denial of service, or DOS, attack. Your system is offline, and they've won. So we constantly have to balance security with keeping the system fully functional. Moving right along, let's look at the types of security requirements, specifically focusing on Firesmith's categories. So how do we systematically defend against these intelligent adversaries? Well, we have to classify the different types of threats to build proper defenses. Donald Firesmith identified 10 distinct types of security requirements that might go into a system specification. Let's methodically run through them. Number 1 is identification. Basically, does the system need to know who you are? Number 2 is authentication, which is how you prove who you are. Number 3 is authorization, detailing what you are actually allowed to do. 4 is immunity, protecting the system against viruses and worms. 5 is integrity, avoiding data corruption. 6 is intrusion detection, which covers mechanisms to spot active attacks. 7 is non-repudiation, and we'll define that one in just a second. 8 is privacy, maintaining data confidentiality. 9 is security auditing, checking how the system is used. And finally, 10 is system maintenance, ensuring authorized changes don't accidentally break our security mechanisms. Now, you won't use all 10 in every single system, but this taxonomy provides a fantastic foundational checklist. Okay, listen up, because here is a direct exam focus call out for you. You absolutely must be able to clearly distinguish between authentication and authorization. Authentication is proving who you are. For example, typing in a username and a password, or maybe swiping an identity card. Authorization happens after you are authenticated. It's proving what you are allowed to do once you are inside the system. Are you a regular user with read-only access, or do you have full administrative privileges to delete files? In short, authentication is identity, authorization is permissions. Keep that locked in your memory. Now let's circle back to number 7 on Firesmith's list. Non-repudiation. Let's define this technically, but keep it simple. Non-repudiation is a requirement specifying that a party in a transaction cannot deny their involvement later on. Why is this so absolutely critical? Well, imagine a modern e-commerce system. If you buy a product or transfer money, the system has to securely log that transaction so you cannot come back later, claim, "I never bought that," and demand a refund. Proving that a transaction definitely happened is the bedrock of digital commerce. Let's do a really quick micro recap before we move on. Just remember, the distinction between authentication, who you are, and authorization, what you can do, is vital. Non-repudiation protects our transactions by preventing denials, And overall, Firesmith's 10 categories give us a comprehensive framework covering everything from identifying users all the way to maintaining the system securely. Now that we know the types of requirements, how do we actually figure out which ones our specific software needs? For that, we use the Risk-Driven Specification Process. This is really the methodological core of this whole chapter. Taking a look at this preliminary risk assessment process diagram directly from the text, you can see how it visually grounds our chronological steps. Notice how it flows so logically from understanding what we have to what threatens it, and finally, to how we define our requirements to protect it. Let's break down each of these interconnected nodes. Let's walk through these steps chronologically. Step 1 is asset and value assessment. What exactly are we protecting, and what is it worth? Step 2 is exposure assessment. What's the worst-case scenario if we lose it or if it gets corrupted? Step 3 is threat and attack assessment. Who might attack us and exactly how? Here, we often use something called attack trees, where the threat is the root, and we branch out to identify all the possible causal attacks. Step 4 is control and feasibility assessment. What technical controls, like advanced encryption, can stop this attack? And crucially, can we actually afford them? There is literally no point in spending $1 million to protect a $10 asset. And finally, step 5 is security requirements definition. This is where we turn those chosen, affordable controls into formal system requirements. So, for a quick micro recap of this risk-driven process, we start by identifying and valuing our assets. Then we assess the threats and potential exposures. Once we know exactly what we're up against, we evaluate feasible, cost-effective technical controls. The final goal is formalizing those chosen controls into written system requirements that developers can actually implement. All right, let's see how this all comes together in a real-world scenario by applying this theory to the textbook's concrete MentCare system example. MentCare is an information system for managing mental health patient records. Based on our risk assessment, we derived some very specific requirements here. For instance, look at the requirement for local patient info download. The why behind this is to ensure continuity of care if the main database is attacked or goes offline. But wait a minute, downloading files creates a brand new risk. So the very next requirement has to be secure deletion after use. That local information must be strictly deleted so later users of that client computer cannot access highly sensitive medical data. We also have log playback for recovery and accountability to ensure we can track who made changes. That last one acts as a really powerful deterrent against misuse by authorized medical staff. And speaking of misuse by staff, that tees up our next major topic perfectly. Section 5, Understanding Misuse Cases and Threat Modeling. This is a massive concept for your fundamental understanding and your exams. Let's define it clearly right up front. A misuse case is basically a model representing an attacker actively trying to break the system or intercept its data. Think of it as the dark mirror to the standard use cases you learned all the way back in Chapter 4. Contrasting them directly really helps. Traditional use cases model normal, authorized user behavior, like a receptionist registering a new patient. Misuse cases, on the other hand, model hostile, malicious adversary behavior. By actively modeling what an attacker actually wants to achieve, software engineers can brainstorm very specific technical mitigations. We are literally stepping into the mind of the criminal so we can build a better vault. Take a look at this diagram showing MentCare misuse cases. On the left, in the normal bubbles, you see our standard use cases, registering a patient, viewing info. But on the right, you see our dark figures, the misuse cases. Here we have an attacker intercepting a transfer, or maybe impersonating a receptionist using a spoofed of server. By mapping this out visually, we instantly realize that a simple password just isn't going to cut it. It forces us to generate a specific mitigation requirement. All communications must use the secure socket layer, or SSL, which uses certificate-based authentication and strong encryption to completely neutralize that interception threat. So, to quickly recap why misuse cases are so essential, they invert traditional use cases to actively model the attacker's behavior. By visualizing the attack, we move from having vague worries about security to generating concrete, actionable technical mitigations that we can actually code into our software. Excellent! We have covered a lot of ground today. Now we're at our lecture summary and review. I'm going to act as your supportive lecturer here. Get your highlighters ready because I'm going to tell you exactly what you need to focus on in your notes for your final test. Here are the core concepts you absolutely must memorize. First, you have to know the exact difference between authentication, proving who you are, and authorization, proving what you are allowed to do.
Second, know the sequential steps of the risk-driven specification process, from asset valuation all the way to final requirements. Third, you must be able to define and sketch a misuse case, showing the relationship between normal use and hostile interception. And finally, always remember the overarching theme of this entire chapter. Security requirements must constantly evolve. Why? Because that intelligent human adversary is always inventing new, clever ways to exploit our systems. We can never just set it and forget it.
We've spent this entire session learning how to figure out what our software shouldn't allow and generating the requirements to stop it. But that leaves us with a massive, provocative question for next time. How do we take these abstract security requirements and actually build them securely into our software architecture? We are going to answer exactly that when we dive into Section 13.4 on secure systems design in our next explainer. Until then, keep studying, stay curious, and I'll see you next time.